And here we start the discussion on Unit 36 about the reaction rate. Yes, at the starting, we will see some reaction is very slow, for example, rusting, but some reaction is very fast. For example, the acid react with carbonate or neutralization. It only takes a few seconds for you to complete. Yes, so how can we first express or how can we interpret the term reaction rate? And here we shows the reaction rate actually is change of chemical or substance over time. Yes, this is the definition. So please highlight this or write it down on your notes. Because only amount is not enough. Or reverse, only time given is not enough. So when they combine, it forms our reaction rate. If you still don't understand, try to think about how to express your running speed. For example, you finish a 100-meter race in 10 seconds. Let me write down. So you can see the speed is here. If you take away the time, it is meaningless. Or if you take away the length of the race, it's also meaningless, right? So the speed is always change of substance over time. Alright, so how can we get the reaction rate in from our experiment is we try to put a graph on the amount versus time. And here is a good example. I try to measure the amount of CO2 within the whole reaction or whole experiment. So you can see for this purple curve, well, yes, it keeps rising and finally it keeps horizontal at the end. So the purple line actually represents the amount of CO2. So we will talk about it later. How can we do it? But if you follow the definition of the reaction rate, then the slope of this graph will equals to the reaction rate. Well, this is another important point for you to understand. If you got such a graph, then the slope will be the reaction rate. If you express our idea mathematically, then will be the tangent of the slope will be equals to the instantaneous rate, right? Because the tangent of the slope will equals to the slope at certain point. And here we introduce two special terms. The first term, okay, before introduction, yes, don't forget to highlight this, right? The first term is called instantaneous rate. So what about the second term? The second term will be the FH rate. So try not to mix these two terms first. Right, before we go further, so have a quick checkpoint to yourself. So how can we express the reaction rate for different reactions? The first one is the mass. Well, the mass maybe this is for solid reactions, right? The second one is concentration. So maybe this involves a reaction about solutions. And the third and the fourth is easy. The volume of gas or pressure of gas, it represents the reaction involve gas. right? So we have plenty expression for the word amount. The amount can be expressed in gram or mole per dm cube or cm cube or Pascal, which is a unit for pressure. And so let's write down. So how can we get the unit of reaction rate? So for the first one is, okay, don't forget the reaction rate is slope. So just y over x, right? So the first one will be gram per second. All right, please stop the video and complete the rest of 3 first before you go further. And here shows. So all of them is y over x mole per dm cube per minute, cm cube per second, or Pascal per minute. So you can see it depends on the reaction rate. You can use either second, minute, or even hours, days, month, or year for your time scale. Right. So let's for the checkpoint 1 and 2, and again please pause the or stop the video until you finish. And here shows the unit of reaction rate. As I mentioned, it must contain 2 parts. The first part is amount. The second part, which is in the denominator, is time. So you can see only the first one. Oh, no, sorry. Only the third one, C, involve the time factor here, right? All right. What about question 2? Is not the unit. Not the unit is, okay, here D shows because you cannot see any time factors here, right? All right. So before we move question checkpoint 3, so we need to back to our concept on instantaneous rate versus average rate. So maybe you have such, okay, let me get a new page first. What should I do? New page. Oh, yes. So so we can see, for example, this is amount. So again, cm cube, this is second. So you can, for the reaction, like this. And you can see, if you interpret the slope as the reaction rate at the starting part, and this is at the end, so you can of course understand at the starting the reaction rate will be faster, right? At the end the reaction rate is almost stopped. So how can we interpret the term reaction rate? It depends on how long you consider. So for example, this is 30 seconds, right? And this is the 5 seconds. So if you consider the first 5 seconds, so of course this will be the slope, right? But if you consider the first 30 seconds, then something will be totally different. So you can see the blue line actually is the FH slope. The blue line will be the FH slope within 30 seconds, right? So of course, after you take the FH, so the slope will be smaller, or the reaction rate will be smaller than that for the first 5 seconds, right? So what about if you shorten the time you consider? 0 to 5 seconds is still too long. So what about 0 to 0.0001 second? Yes, if you shorten the time, then the FH rate will become, sorry for the poor handwriting, instantaneous rate. So if you got the idea of differentiation, so you will know it better. Okay, so how can we get the instantaneous rate is a big trouble, because for example, I want to get the instantaneous rate in the 15 seconds, so I need to draw a tangent and then calculate its slope, which is a big disaster. So don't worry, you will not asked to do so in your public exam. Because it's too time consuming and it is difficult to judge whether you are correct or not. So instead, they will provide the slope, right? They will provide the slope. Oops, sorry. They will provide the slope like this purple line, and then ask you to calculate the slope. Okay, they provide the tangent. They provide the tangent and ask you to calculate. This is the instantaneous rate. So what about the calculation of FH rate? Easy. Just calculate the change of y over change of time. It's okay. So this is the difference between the FH and instantaneous rate. And now you see question 3. Well, we have A, B, C, D, 4 slopes. A, B, C, D, 4 slopes. And which of them is correct? Right, you can see first reaction rate, slope A. Slope A, the slope is the highest one. So, sorry, it should have the highest. Right? The second, what about B? B is the initial rate. So, what is mean by the term initial? If you study physics, it will be better. Initial means time equals to 0. That is the starting. So of course not, because for the B, it represents time A, time t1, right? Time t1. Sorry for that. C is the instantaneous rate for time 2. T2. T2 is here. For this point, it makes sense, right? This is C. It makes sense. What about D? Well, D should be the instantaneous rate for T3. So it is not the FH rate. From the commandments again is start. Yes, I tell you the truth. I learned this word from the morning assembly. The MC on the stage always say the assembly is about to commence. So yes, the answer is C. This is slope D is not the FH rate. Slope D is actually the instantaneous rate for T3. Right. So in exam, so for example, you are given this equation. Now, but we need to consider within the following minutes, you will recall the concept mole ratio. Okay, mole ratio. All right. For this equation, 2 N2O5 will generate 4 NO2 and 1 O2. Now remember, the mole ratio is 2 to 4 to 1. So you can expect, if 2 N2O5, this is the first step. If 2 N2O5 is for 1 O2, so we highlight N2O5 and O2. So you can expect that the reaction rate for O2 will be higher or smaller than N2O5. Right, of course it is smaller, right? Because you need 2 N2O5 for generate 1 O2. So the consuming of N2O5 should be higher than the producing of O2. This is a simple mole ratio questions, and they should have the ratio in reaction rate 2 to 1. Okay. Let me write it down. Rate of consuming N2O5 equals to rate of forming O2 times 2. So we can get this from the graph. Okay, we consider the FH rate between 300 and 400 seconds, and we got this idea. Okay, right. Some of you may wonder, what about the negative side? Well, the negative side is because as a reactant, so N2O5 will keep dropping, so their slope will be -1, which is tailor-made for reactant. And if you consider the product, then very good, their reaction rate will be positive, and that's it. Okay. Well, next one is what about the reaction rate between NO2 and O2? Now, both of them are product, but when you produce 1 O2, you will produce 4 NO2. So their relationship will be like this. And again, this is reflected on the real values. So finally, what about NO2 and N2O5 and NO2? Well, 2 to 4, so it looks more complicated, right? and let's write it down. Rate of forming, oops, not forming, is consuming Alright, so if you have no idea the ratio, which one should be times 2, which one should be divided by 2, okay? So first, my hint for you is don't use divide. Always use multiple sign, which is easier for you to handle. The second one is before writing any sentence like this, okay, before writing, so ask yourself from the mole ratio, which one will form faster? Well, in our example, N2O5, okay, N2O5 and NO2, which one will form faster? So of course NO2, because it got 4 in the coefficients, right? So NO2 is faster. NO2 is faster. So originally it should be like this, right? Originally. But now we simplify our case like this. The formation of NO2 will be double to that of consuming N2O5. And again, this is proven by our data. Right? So I hope all of you will understand the relationship between forming and consuming within this equations. Okay? Finally, a very special term for this one is, let me use another color. It's a very special term, is rate of reaction. If we consider this chemical reaction, okay, so how can we interpret? Equals to, so how if the reaction rate of this reaction, how can we express in terms of N2O5 or in terms of NO2 or in terms of O2? So again, try to think about it by yourself and stop the video first. Well, the final hints before you stop the video I can give you is when we undergo one reaction, then you need to consume 2 N2O5, forming 4 NO2 and forming 1 O2. So try to elaborate the relationship. Now here is the first hint for you. Yes, so many students feel confused why the reaction rate equals to half to that of consuming N2O5. So I use a new page again. As I mentioned, whenever you do one reaction, then you will consume 2 N2O5. That means the consume rate of N2O5 should be faster than the reaction rate, right? So that's why we have such an idea is reaction rate equals to half consuming N2O5. Yes, right? And we can go further. So what about in terms of NO2? When you complete one reaction, you will form 4 NO2, right? So the reaction rate will be only a quarter to that of rate of forming NO2. And finally, I'm sure you can get it, right? Yes, so the reaction rate like this. And this is a bit difficult for students to handle. Why suddenly there is a new reaction rate here? And I hope all of you can get it. Okay? Right. So next one is we have completed this already. So how can we interpret the FH rate is always change in amount versus time taken. So this is time taken, this is X, this is change, this is Y. So Y over X equals to slope, right? Good. But for the instantaneous rate, now this is FH, okay? But for the instantaneous, so you need to draw the slope of tangent at exactly certain time point at exactly. So again, as I mentioned, no need to spend time in drawing this. Okay, you will be given. So just calculate. It's fine. But there is an important point. Is we will have a special name for the instantaneous rate at time equal to 0. This is very important. Okay, it is called initial rate. So next time when you see the word initial rate, actually we are talking about the instantaneous rate at time equals to 0. Well, the importance of initial rate is that is highest concentration. The reactant, oops, poor handwriting again, right? Reactant. The reactant got the highest concentration. That means the reaction rate also be the highest. Okay, and this is the scientific meaning of initial rate. Okay. Alright, so again, this is chapter 1. So please do it by yourself, and I will give you the answer later. And again. Wow, good. I want everyone to do this now. First, please. Oops, sorry. 5 and 6. Sorry. Yeah. The this one is easy, but 5 and 6 is a bit difficult. So please do it now. Well, you can see consuming, okay, decomposition means consuming, right? Consuming of NO2 is this one. So what about the formation of O2? They have ratio 2 to 1. Now first ask yourself, the formation of O2 will be faster or slower than the consumption? Which one will have faster rate? So you need 2 NO2 to form 1 O2. Right? Of course, the O2 will get slower rate, right? It is not easy, a lot difficult to understand. That means the rate of formation of O2 should be less than 3.2 times 10 to the power minus 3, right? And you got only one choice, is A. Now with the same idea, please complete question 6. So first, the rate of N2 sodium carbonate is here. What about the form CO2? Now, this is 2 to 2, this is 2 to 1. So A is not correct for sure. It is nonsense, for they don't have the same rate, right? 2 to 2. The second one, part B, we need 2 hydrogen carbonate to form 1 sodium sulfate. So hydrogen carbonate should consume in highest rate, right? So it makes sense. It makes sense. C is sulfuric acid to sulfate. Sulfuric acid is here, sulfate is here. Again, it's 1 to 1. That means they should have the same rate, right? Finally, is sulfuric acid 1 to CO2, which is 2. So the rate of formation of CO2 should be higher. So again, this is not correct. Because when you consume 1 sulfuric acid, you will form 2 CO2. So the formation rate of CO2 should be double to that of sulfuric acid. So our final answer will be B. Right. So we will take a break here. So please stay tuned for the part 2 in Unit 36.